recognition.
Landing legs have deployed, and Falcon 9 has landed. Dragon, separation confirmed.
Houston Station, space ground to ISS thrusters enabled.
Houston Station, Dragon hatch opened at 13:07. On behalf of Ripley, Little Earth, myself, and our crew, welcome to the Crew Dragon.
Houston Station on 2, ISS crew is ready for departure. Separation visually confirmed. We have visual on Joe. We have 4 healthy sheep.
Recover this is dear Steve. Dragon has landed.
Hi, welcome to the August meeting of the San Diego Astronomy Association. That little video was from the SpaceX Crew Dragon, which was their mission to take astronauts back to the International Space Station, although that was actually the video of the flight just before they took up the 2 astronauts and brought them back. That was kind of the test run. So it was a nice little short video showing the return technology for taking astronauts back to space, which so I thought was really cool. One of the neat things that's happened in the recent past, so I thought I would show that short video. And then next, kind of onto our club business. Of course, the San Diego Astronomy Association has a calendar where we maintain all of our events. You can type in SDAA into Google, and we are the first thing that comes up in Google. Go to our webpage. There's a calendar available right there for you to consult with, and we have other things that are also available. Of course, we have our Facebook, Twitter, and Instagram. I got a nice meeting announcement via Instagram yesterday. And Dave, if you would put up the link to our Loaner Scope program for those of you who don't have telescopes or are just kind of starting out, they're interested in borrowing a telescope from the club free of charge. But, we expect you to, it's like a 3-month Loaner Scope, bring it back in good working order. But it gives you a chance to try out astronomy without having to dive in and buy something kind of expensive. I don't yet see the link up. Dave, did you get the link I sent you for the Loaner Scope webpage?
You mean that one?
Yeah, so you can see if you open the chat window on the Zoom, you can see that Dave has put up a link, so you can just copy and paste that into the any web browser, and it'll take you right to our Loaner Scope program run by Ed Rumsey. And you can contact him if you need a scope. So it's really nice service that the club provides, really helpful for new members. In addition to that, we have a newsletter that we maintain. And the August issue of the newsletter is now out, and it's on. There's a great article in there on the Summer Triangle and all the various astronomical things that are up in the sky at this time of year. So I'd encourage you to go take a look at that. And there's a link also, Dave. Would you put that in the chat also? There's a link that'll take you right to the place where we keep all of our newsletters, so you can. When between our meetings here, you can go take a look at them. Interesting reading, and so you can see that link is up there now. You can just copy and paste that into your web browser, takes you right to it. So otherwise, you know, you can go just to the web page and you navigate through the links, and they're all there, and they're fairly clear, but it's kind of nice. We'll get you right directly there. So if you'll take us to the next chart now. Okay, so we also have a merchandise store. So if you want that new summer item you've been looking for, or you're getting ready for your fall astronomy observing, you want an SDAA hat or hoodie or other items, we have a SDAA merchandise store, and Dave's going to put the link up in the chat for that. And there it is. So you can just copy and paste that in any browser, take you right there. Take a look at the kind of items that we have. See if there is something you've always wanted but never knew it. Next chart. Is a nice video. So
last summer, an amateur astronomer discovered the first interstellar comet zipping through our solar system, 2I Borisov. It was clear from its path that the comet would dim from view within months, so scientists were quick to turn their telescopes towards the alien comet for a view. Among them was an international team led by NASA Goddard. They used the ALMA telescope array in northern Chile to probe 2I Borisov while it was close by. Inside the halo of gas around the comet, they detected something peculiar. 2I Borisov was releasing a higher concentration of carbon monoxide than any comet observed at a similar distance from the Sun. NASA's Hubble Space Telescope later confirmed this too. Scientists wondered, could this be our first glimpse of the chemistry of another planetary system? Or are we learning that there's more chemical diversity among comets than we knew of? Carbon monoxide is one of the most abundant molecules in space. Scientists expect to see it inside all comets, yet there's a huge variation, which is puzzling. Regardless, 2I Borisov is off the charts. To preserve its carbon monoxide, the comet likely formed very far away from its star in one of the coldest environments known. In our solar system, this would have been in the vicinity of Neptune. When comets were forming, temperatures there could have reached negative 420 degrees Fahrenheit. Scientists think that gravitational disturbances from young, jostling planets may have thrown 2I Borisov out of its home star system and onto a cold, lonely voyage. Our solar system is tiny compared to the distances between star systems. It's incredibly rare for an interstellar comet to pass within observable range. However, big, sophisticated telescopes are coming online, so scientists expect to see more alien comets like 2I Borisov. Will they all be similarly exotic?
So that's kind of cool, and I think these are kind of neighbors to Dr. Nick, who's going to talk tonight. So I don't know, maybe he has some further insight into that facility. It might be kind of cool to hear about too. Our next video is there's this group on YouTube that goes out and pulls archival Apollo footage and upgrades, does upsampling and increases the frame rate and does some beautiful work from giving kind of a new perspective to this old imagery. So if you'll run that video, I think that's really cool.
Yes or no? No. Okay. I can get it now if you like. Yeah, get it. Okay.
Rover, this is Houston.
Fast J293. Go ahead, Houston.
Dave, we want you to head towards Station 4, and we'll advise you on what your rate looks like and the tasks that we want you to carry out once you arrive. Just start off in the direction of Station 4, please.
Taking me heavy. I can see it over there, Dave. Yeah. I see about 330. But that's not going to mean much to you until you get down to the level. That's right. And the camera's running, Joe.
Okay, and standing by for a mark when you roll.
We're rolling.
Roger.
Hey, your camera. Camera's loose on a swivel, Jim. No, I'm getting a pan here. Oh, really? Oh. It's an awful fast pan. I just wanted to make sure it was running.
Dave, you'll want to trend or course.
We jumped out of the video a bit.
You've all probably seen it on TV. The largest crater, which was Arrowhead, we named Arrowhead, really runs east-west, which we mentioned before, rather than north-south. And on the northern side of the large crater, a Longate crater, which runs east-west, on the north side, there are a great number of blocks exposed.
Roger, we copy.
Tracks here as we go down slope. Rover tracks. Yeah, probably just follow the tracks, huh? Yeah, probably do.
Sounds good.
We know that's a fairly good route. Yeah. Okay, we're heading 320, bearing 350, and range is 4.3.
Copy, Jim. Thank you.
Sure, it's bouncier going down, isn't it? Yeah. Yeah, we're back down out of it now. What a beautiful sight. Man. Oh, we didn't get the 500 stereo up there, but you got a pan, didn't you? Yeah. Okay. Well, I can't get over those lineations, that layering at Mount Hadley. Well, I can't either. That's really spectacular. It's beautiful. Talk about organization. Yeah, man. That's the most organized mountain I've ever seen. Yeah, they're so uniform in width, you know. Nothing we've seen before has had the same thickness of each bed. Uniform thickness from the very top to the bottom. Yeah. And looking to the north on that spur that we talked about yesterday, we can see the horizontal beds again.
Roger, Jim. Copy. Any idea of the dimension?
Actually, I'd estimate it's relatively thin, but yeah, I'd say it's probably, if you took the ridge line on Mount Hadley, which is practically horizontal at our present position, and split that into 100%, then I'd say those lineations across there, the bedding across there, are probably like 0.25%, wouldn't you, Jim? Yeah, certainly less than 1. Yeah. Must be, if you look across the ridge line and then look at the dip to the northwest there, you could count a couple hundred anyway, could you? Apparently you couldn't see that on TV.
No, not at all. Not at all. Hopefully it's in the photographs, but we're marking it down nonetheless. TV, it never...
And then if you look, Jim, horizontal half, well, all the way up. I guess that would be slumping. Yeah, there is. I see it now, yeah. It just looks like slump, probably. Yeah. Because they're discontinuous sub-horizontal lines, which are pretty much cross-bedded. If it was bedding, I don't think it is. It just looks like slump pattern ground.
What kind of progress are you making now, Jim?
We're going at about 0.8 clicks. No, 8.
Roger, copied 8.
That's almost backing up. And we're heading 340, bearing 349.
And Dave, could you back up one slide? We actually skipped over the previous slide. Yeah. So if you could play that video.
Great. I guess you're about the only person around that doesn't have TV coverage of the scene. That's all right, I don't mind a bit. How is the quality of the TV? Oh, it's beautiful, Mike, it really is. Oh, geez, that's great. Is the lighting halfway decent? Yes, indeed. They've got the flag up now, and you can see the stars and stripes on the lunar surface. Up now, and you can see the stars and stripes on the lunar surface. Beautiful, just beautiful. See if you can pull that end off a little bit. Straighten that end up a little. It won't go out. Okay. EMU flight.
Flight EMU.
How you doing?
Well, we're slipping another 10 minutes or so. We're down below our nominal, but we're not to our go-no-go points.
Okay, Capcom flight.
Good flight.
Get a comm check. Must be talking.
Who?
The crew. Neil or Buzz.
Neil, this is Houston, radio check, over.
All right, Houston, loud and clear.
Roger out.
Loud and clear, Houston.
Roger, Buzz.
Flight count.
Go.
Columbia.
Roger.
50 years ago. Okay, Dave, if you can move us forward 2 slides. Cool one on the SpaceX version, one more, yeah, there, of the new spacesuit. So you can compare them to what you just saw from the Apollo astronauts. So go ahead with the.
I think one of the things that was important in the development of the suit was to make it easy to use, something that the crew just has to literally plug in when they sit down, and then the suit kind of takes care of itself from there. So the suit is really kind of one part of the bigger Dragon system. It's really part of the vehicle. So we think of it as kind of a suit seat system. So the seat that the crew is in and the suit are in a lot of ways working together. And so it made sense that we were designing Dragon in-house to also design the suit.
Our spacesuit is completely designed in-house. It's built here in Hawthorne, California, in the same building as the rocket and the capsule. The spacesuit is custom-made for each crew member, and that is to optimize the fit for the crew member.
We definitely wanted to innovate, and we wanted it to look inspiring, but first and foremost, we wanted it to be safe and reliable. The spacesuit's primary purpose is to protect the crew in the unlikely event that the cabin were to depressurize. But the suit does a number of additional things. It provides cooling and communication to the crew inside of the suit, it provides them hearing protection, and the outer layer of the suit is flame resistant, so it provides flame protection as well. When the crew gets in the capsule, they get in their seats and they plug the suit into the umbilical that's attached to the seat. And the umbilical is providing everything that the suit needs. So it provides the avionics or electronics for communications. It's providing the air to cool the suit, and then it also provides gas when needed to pressurize the suit. So it's really a single point that lets the suit do all the things that it needs to do. We designed the helmet in-house. The helmet serves a number of different functions. Obviously, it's protecting the crew's head and it's retaining gas like the rest of the suit, but it also houses the microphones as well as the valves that are regulating pressure in the suit. We had to design the gloves so that they would work with the touchscreen so that the crew could use the touchscreen while they were in their suit. But the gloves also still had to do a number of other things like the rest of the suit. And then, of course, they have to be able to work under pressure. I think one of the things that's cool about the suit is it's not just a piece of hardware, it's not just a suit. It's a very personal thing to work on for everyone on the team who's been building these, and so it's a really amazing thing.
I thought this was really cool. It's so different from the other spacesuits, plus these are the ones that the two astronauts actually wore, this style, to the International Space Station over the last month or so. And returned. So it's kind of a cool look at what the future might mean in spacesuits, which is a whole just cool thing all by itself. So next chart, please. So we have many incredibly talented semi-amateur, semi-professional astronomers, and they take just a wide range of gorgeous imagery. And so this one, so every month I pull a few of them and pry one of their little gems out of their hand. And so Carl is one of the most generous people sharing his work. And so he took this one of a supernova remnant, which is, you can see the kind of blue bottom of the bubble, and you can't really see the top of the bubble very much there, for this supernova remnant that he took with 13.3 hours of exposure. A lot of this astrophotography stuff is incredibly technical, but it ends up with products that are incredibly beautiful. And even if you're not a technical person, you can enjoy the beauty and aesthetics of what they turn out. So I think this is another wonderful example of that kind of thing. On the right is some technical information about the hardware, software he uses to do the creation of this image. So you can make note of that if you're interested in trying to do similar types of things. And our next slide is another picture that Carl sent me, and of a planetary nebula. So this is a star that's dying, that's throwing off the outer layers of its gas in a bubble around the central star. You can see it's a great name there, PNG 75.5 plus 1.7. So that's a kind of traditional astronomical target name. But it's again aesthetically beautiful. This one particularly challenging because it's very dim, and so you can see Carl built this picture with over 45 hours of exposure time. So that's many nights collecting data and then processing on some fairly sophisticated software, PixInsight, which is fairly commonly used amongst many of our amateur astronomers, and in most often discussed in much more detail in our ASIC meeting that occurs 1 week from tonight. Although next week is a different topic, there's going to be a review of a new kind of telescope, and I will be presenting that meeting also. And so if we can go on to the next slide, which is tonight's digital door prize. So Dave will put a link in the chat. Thank you, Dave. So this is a little thing that many astronomers already have. So when they go to clear nights, they want to know, is it going to be cloudy? And if it's not going to be cloudy, or is it going to be clear, or is it going to be, is the sky going to have a lot of humidity in it, so I can't see through it, or is it going to be very turbulent so that the stars wiggle and dance around quite a bit? So, and that's what this free online tool is. So if you cut and paste the link that Dave just put into the chat, you can look up, in this case it's for San Diego, but for any of our friends that joined us from Orange County, I believe there's links further north even to get even closer to where you are. And it'll show you things like when it will be cloudy. So they have, this is done by a guy in Canada, actually, I believe, and he uses regular meteorological data from the Weather Service to predict every day when he hit the clouds in our local area, how much humidity will be there. In fact, so down in the bottom, like the little squares are once an hour, and they're color coded. And if you scroll around on the page where you find this thing, it'll tell you what each color means. And when it's cloudy, it means it's either cloudy or partly cloudy, or if it's humid, it's like slightly humid, or if it's very humid, then of course you'll get dew condensing out on your eyes and things like that. So it's a nice little free online thing if you want to think about staying up and doing some photographing of the sky or something like that, or just even going out to look, and you want to know, is it going to be clear tonight and for how long? Just go to this little thing and it gives you some guidance for a little bit more than you'll get like a phone, like your normal weather app on your phone. So that's kind of the link for that digital door prize tonight. And then we have one more video, which is our next slide, which is kind of setting up and talking about what is the Big Bang, and kind of putting in context of what we know about it. And so it's a really cool YouTube video by experimental quantum physicist. So Dave, if you'll play this video, this will set us up for this will set us up for our next speaker, Dr. Nicholas.
There are many descriptions of the Big Bang out there that are wrong. Anything that says the universe exploded from an infinitely small, dense and hot point, known as the Big Bang singularity, are out of date. But I've seen this description in many places, in diagrams and on the internet. I've even been guilty of saying this too. But I've recently updated my understanding, so here's what cosmologists actually mean when they say Big Bang. We start about 13.8 billion years ago, when space was much smaller than it is today. For the sake of illustration, I've drawn the early universe as this little ball, but there's some caveats to this picture which I'll clear up later. In this tiny universe, space is very tightly curved, so if you travelled in a straight line, you wouldn't have to go far until you got back to where you started. The universe doesn't contain any stuff yet, no matter or radiation. It's just pure space, and this space has energy. The universe expands exponentially in a process called inflation. This means that it keeps doubling in size, so it would take you longer and longer to do your round-trip journey, which means that the curvature of space is getting lower and lower until space got so big it was essentially flat and you'd be walking forever. And then there was an end to inflation. The energy inherent to space was turned into stuff: matter, antimatter, particles, and radiation. This is known as the Hot Big Bang, and this is where all the matter in the universe came from. Even though inflation stopped, space was still expanding, so over time this matter became less dense and less hot. First, there were just fundamental particles. Then after a microsecond, the quarks condensed, creating protons and neutrons. Then a second later, neutrinos stopped interacting strongly with the other particles and flew free. Then, after a few minutes, matter and antimatter annihilated each other, mysteriously leaving behind some leftover matter. Then, protons and neutrons came together to form the first atomic nuclei of helium. Then, after about 379,000 years, we reached the end of the Hot Big Bang, when hydrogen and helium nuclei captured electrons, forming the first stable atoms, and photons stopped interacting strongly with the other particles, and flew free as well. We can see these primordial photons today as the cosmic microwave background. After that, the universe behaves in a more familiar way to us. Slight unevennesses in the distribution of matter means that gravity pulls matter into clumps, which after about 100 million years get dense and hot enough to start nuclear fusion and the first stars shine. Then, 600 million years later, the first galaxies form out of collections of stars. After inflation, the expansion of space slows down and keeps slowing for many billions of years. But today we see that the expansion is accelerating again, and we call whatever's causing this accelerating expansion dark energy. We also see that matter is very clumped together in galaxies and galaxy clusters. And that's the story of the creation of our universe. So why is this our model of the beginning of the universe? It's because this is the best description we have that matches the things we observe in the universe today, like the distribution of stars, galaxies, and the temperature of the cosmic microwave background. The cosmic microwave background is a key piece of evidence about the early universe because it says that everything in the visible universe, everything in the massive radius of 46.5 billion light years, must have been in thermal equilibrium at some point in the past. This means that it must have all been packed into a tiny space and had time to all be at the same temperature, before everything moved away from each other by the expanding space. The best scenario we have to explain this is cosmic inflation. The old Big Bang singularity model predicts other things like large temperature fluctuations, which we just don't see. So this idea that the universe exploded out of an infinitesimal point was thrown out 40 years ago. Now, my description of inflation was a little oversimplistic. I did that on purpose to get the main ideas across, but I need to clear up a few points. When I said that the universe started off being really small, that only applies to the patch that became the visible universe today. But this visible universe is only one section of a much larger universe, and we don't know how big that larger universe was, or is. Also, I drew the early universe as being a tightly curved ball, but we don't know if this is true either. All we know is that if there was any curvature to space before inflation, inflation would have made it flat. But space could have been flat before inflation, we just don't know. And we're not even 100% confident in this inflation hypothesis, it's simply the best idea we have so far that fits the observations. And unfortunately there are hard limits to what we can ever observe and know. You probably know that the further away in space you look, the further back in time you're looking. So that means the earliest light we can see is from recombination in the form of the cosmic microwave background, so we can't see further back beyond 379,000 years after the hot Big Bang by using light. Potentially we can detect primordial gravitational waves from before this time, but this will need a huge space interferometer. And even with the most idealized experiments we can conjure up in our minds, we could only ever probe the last fraction of a second of inflation, 10 to the minus 33 seconds. We can never see further back than that because the information simply doesn't exist in our universe. But the takeaway point is when cosmologists say Big Bang, they're usually talking about the hot Big Bang, which is a period of time after the end of inflation stretching for about 379,000 years. So you might be wondering, what happened before inflation? What actually started the universe? Although lots of people are thinking very hard about this, it's still a big mystery. We don't know how long inflation lasted, we don't know what existed before inflation, we don't know how big the whole universe is, and we don't know if time started or if time has existed forever. And perhaps we'll never know the answers to these questions. But I have a feeling that's not going to stop us from trying to work it out. I'd like to give a big shout out to Katie Mack for helping me understand some of these concepts. She's really good at explaining cosmology and astrophysics, so you should go follow her on Twitter. Also, I'm doing a run of these Big Bang posters. Check them out on my store on DFTBA. Thanks again for watching. See you next time.